So, putting everything together now. So we want to solve initial value problems using Laplace transformations. Now, out of all the ones we've done so far, this is actually what I think is one of the easiest and the favorite ones a lot of people use. That's why it's so popular. If you like partial fractions, this is going to be a winner. If you don't like it, then it's probably not so much. But if you get around the partial fraction part, it's actually much easier than you may think going forward because it's not a lot of derivatives integration. It's just pretty straightforward. This is what we want, we transform it to this stuff here, we do everything we want in here, and then we just back it there, right? You do the inverse and we get our answer. It depends on the person, but a lot of people really like Laplace because it's very smooth transformations. So how do we solve to doing it? Roughly 3 steps. The first 2 are pretty straightforward. So take the Laplace transformation of both sides of the equation, use the properties of Laplace and initial value to solve for L of y. Okay. And then we just go to re-engineer everything we have. Okay. And you'll see how that's going to go about. Most of the work is just getting the inverse of it. Manipulating the Laplace for s into something we already know, and then just going backwards using our tables. Okay. So look at this one. So for example, so solve for the initial value problem. So normally, right, we would solve for the homogeneous part, and the particular equation, and then put them together. But we can just bypass all of that information and go straight using Laplace, and you'll see how that's going to go about. The work is roughly the same, but again, there's no have to solve for 2, then this and that kind of situation. So if you want to transform this entire thing to Laplace, so it's a double prime, so it'll be L of y prime minus 2 times L of y prime plus 5 L of y, and on this side, negative 8 L of e to the negative t. Okay. Now at this point, it's just using the properties we have of Laplace. Okay. So most of the time, we can just break stuff down. So using the derivative of Laplace, this is equal to s squared L of y minus s of y of 0 minus y prime of 0. And same framework applies for the first prime. It is just this part right here. Like that. So the initial value goes here, there, and there. So this is a constant. That's what we're eventually going to be solving for. Minus s times y of 0, which is 2, minus y prime of 0, which is 12. Okay, so this is the second derivative part. And the first derivative part is going to be s times L of y minus y of 0, which is 2. And this is just going to be itself, right? That's not changing anything. So now resubstituting everything where it's supposed to be. So this part here gets replaced with that, and this part here will get replaced with that there. And I'll talk about the right-hand side in a little bit, but just do the left for now. So now we have s squared L of y minus 2s minus 12. This is for the first part. And then minus 2 times the distribution of this. And this becomes positive 4. And then finally plus 5 times L of y for this part here. Okay. Now on the other side, we just use the tables to find the Laplace transformation of e to the negative t. So e to the negative t, this means a is negative 1. So the normal one is, I believe, this part. Or this is going to be a here, s of minus a. So because a is negative, it becomes positive, and multiplied by negative 8, so it'll be negative 8 over s plus 1. Okay. Now the whole point is to solve for this. So let's collect like terms and move everything around. So pull L to Y, so this will be here. And yeah, so minus 2s of this, and then plus 5. And then put everything together we have as well. So I can put this and this together, and this is going to be by itself. So that gives me negative 8. Okay, so now I'm going to bring all of this to that side, so I'm just going to add both of over. And I'm going to simplify this a little bit by foiling out, or just factoring out the L of y's. Like that. Okay. So I'm now going to put this together. So I'm not going to bore you with the process, right? You just common denominator, so multiply both of them by s plus 1, top and bottom, and eventually you get this. And then lastly, I want this by itself, so I would just divide this over. So we finally get the Laplace transformation we're actually looking for. So it's our job now to figure out what is this transformation and just regenerate what we had to begin with. So this goes back to a couple of rules. So notice I can complete the square here. So if I complete the square, that means it's me minus 2 over 2 squared. And that's just going to give you 1. So I add subtract 1 to both sides. Or not to both, so I add here and subtract 1. So this ends up being a perfect square in the bottom of just s plus 1 squared. And this 1, so the minus 1 minus 5 is 4. So plus 4 here. And this whole thing times another s plus 1 there. Okay. Now, looking at our tables, this looks like sine and cosine. If we just make this a little bit bright, so this will be A, B, and we got to figure out the top situations. But we have partial fractions, being this is one of our partials, and this is the other one. So this is where the fun stuff comes into play. So going back to partial fraction decomposition, this is going to end up being A times s minus 1 over the original part, or plus, let's say 2b, because of the, yeah, I guess because of that. Yeah. And I'm going to put this as 2 squared, so it looks identically like it. So this follows a template as A being negative 1 and B being 2 in this template. That's why the 2 is there. And then plus C times over the other partial fraction decomposition. Okay. So breaking this apart, I could break this up even more if I really want to. So I can split this apart. So I'm just going to look at the top just for now. Like that. And then these two will have the same denominator. Okay. So again, partial fractions, you just multiply what's missing. So on this side, what I'm only missing is another s plus 1. So I multiply these both things by another s plus 1. The c value multiplied by all of that bad boy. Okay. So eventually, after a lot of simplification and stating which one goes where and solving for it, we eventually get A is equal to 4, B is equal to 7, and C is equal to negative 2. So, how do we do this inverse Laplace stuff? So, going back to our process, go over here. Be a 4 on the outside. And now we want to find the inverse Laplace of s minus 1 over s minus 1 squared plus 2 squared plus the b part, which is 7. So 7 times L Laplace inverse of just 2 over that exact same portion. Oh, yeah, this should have been minus. Yeah, there you go. And then plus the c part, negative 2 times the inverse Laplace of just 1 over s plus 1. And now we just look at our tables, and this one ends up being cosine, or more precisely e to the at times bet, and this is going to be the sine of it, and this is just e to the t. So our final answer will be 4 times this part, so 4 times e to the, and a in this case is 1, so it'll be e to the 1t cosine of b in this case is 2, plus 7 times the exact same thing of the sine, and then minus 2 times this part. And this time a is going to be negative 1. And there's our answer. So again, the tricky part is the partial fractions, but I don't know, to each their own. So let's try another. Okay, so same situation. Step 1 is just reversing everything. So same definition as we did last time. So this is going to be itself. I'll just put L for short, running out of space here. This is going to be 0, sorry, 0. This is 1, so minus s. And this is going to be 0, so minus 0. And this is going to be 1, so minus 1. Okay, and so rewriting everything, so it'll be this part plus 4 times this part minus 5L. And on the other side, we have t e to t. So that one's going to look like, well, in this case, a is going to be 1. So it's going to be, and n is going to be 1 as well. So it is 1 over s minus 1 squared, because it's the factorial one. It's the n factorial over the n plus 1 situation. Okay. All right, so now we follow the same process. Like bring all the L's and everything else on one side. So we have that, and that. Again, about the same process we did last time. Bring this over. And this one actually factors nicely. And bringing this over and then collecting everything like terms gives us this. All right. Now, dividing this all over. Okay, so we have s plus 5, and we have 3 powers of s minus 1 now. So we're going to have repeated roots. Okay. So we're going to have a over, we'll do the first one, s minus 1, s minus 1 squared, and to now the third power. And the last one we'll call d to be just a 5. Like that. And now, again, same process. So this I would multiply by s minus 1 squared times s plus 5. This one I would multiply by s minus 1 times s minus 5. This one just this one. This one times that one, right? And eventually, after a lot of algebra, we get these as our answers. Now the best part is, remember, these are all constants. So the reverse Laplace is literally the bottom ones, what we really care about. Right? That's the main ones we care about itself. And these are always going to be e to the x's. It's actually a tribute to this itself, depending on the situation we have. The only one that's going to be a little different, where we're going to tweak a little bit, is going to be this one right here. But it's about the same thing because we have the cube here. So this is just nice e to the x. This is a t e to the x, which notice it's that one here actually. This one is not so fun to deal with. So I'm just going to show you guys how this is going to work. Now we don't actually have a reverse Laplace for this one. That's the problem. So I'm going to have to force it by using this process. So the reverse Laplace basically has n factorial with an n plus 1. We don't have that here, so I'm going to force it. So I'm going to multiply this by 2. So if I multiply this by 2, this now becomes 1/12 times 2 over that. Which makes sense, right? If you simplify, you get 1/6. But now notice this now becomes as an n over, oh yeah, n factorial actually, yeah, n factorial, n minus 1 to the n plus 1 power. So it works using this process here now. So it's going to be a t squared instead. Okay. So that's a little tricky part for that, but all the other ones follow the exact same pattern as this one here. So for example, my reverse Laplace, or the y value, will be 181 over 216 times e to the t plus, or minus this time, 1 over 36t e to the t, because t is 1, or a is 1, plus, and now this is the situation we have here, so it's going to be squared instead. And again, I have to use the 1/12 because this is the actual reverse Laplace here, this including the 2. So be t squared e to the t. And then finally plus the last one with the d value. And this one now a is going to be -5. There we go. Okay, and that's how we do solving using the Laplace transformations. Pretty interesting. One of my favorites to do so.